Imagine a place in the universe. It is a place of absolute darkness, a perfect sphere of nothing. But this nothingness is not calm. It is spinning, faster than you can possibly imagine. This spinning monster is a black hole. It is so heavy, so dense that it pulls everything towards it. Nothing, not even light, can escape its grip. But its power is even stranger than that. This spinning giant does not just pull on things in space, it grabs space itself. It grabs time itself. It twists them into a cosmic whirlpool, a vast and silent storm. This space-time vortex defies intuition. Over 100 years ago, a brilliant scientist named Albert Einstein had a revolutionary idea. Before Einstein, we thought of space as a big empty box. We thought of time as something separate, always moving forward at the same speed for everyone. But Einstein saw things differently. He imagined that space and time were not separate at all. He believed they were woven together into a single four-dimensional fabric. Einstein's theory, called general relativity, explained gravity in a beautiful new way. He said that massive objects like our sun do not pull the Earth with an invisible force. Instead, the sun's great mass creates a dip in the fabric of space-time. The Earth is simply following the curve in space-time created by the sun. Imagine placing a heavy bowling ball onto a large, stretchy sheet. The ball creates a deep well in the sheet. If you then roll a smaller marble nearby, it won't travel in a straight line. It will circle around the dent made by the bowling ball. This idea was tested and proven. During a solar eclipse in 1919, scientists saw that the light from distant stars bent as it passed by the sun. This opened up a whole new universe of possibilities. If space-time could be bent, what else could happen to it? What would happen if an object was incredibly heavy and spinning incredibly fast? Einstein's equations showed that a spinning object should do more than just create a dip in space-time. It should also drag space-time around with it. It was like a spoon stirring honey. Frame dragging suggests that space and time are not static. They can be pulled and twisted by moving objects. Imagine our Earth. It is a big, heavy ball, and it is spinning. According to Einstein, as the Earth spins, it should slightly drag the fabric of space-time around with it. We are all living inside a very, very slow space-time whirlwind. It's a silent, invisible motion that affects everything within it. Now let's imagine something much heavier and much faster than Earth. Let's imagine a black hole. A black hole is the collapsed core of a giant star. When this super-dense object spins, the effect of frame dragging becomes extreme. It doesn't just gently stir space-time, it creates a violent vortex. This is the space-time tornado. It is a region of space where space-time itself is swirling around the black hole at incredible speeds. Inside this space-time tornado, the rules of direction get confused. Imagine you are in a spaceship near a spinning black hole. You try to stay perfectly still, but you can't. You'll be forced to move because the space you're in is moving. Near a spinning black hole, there is a region called the ergosphere. Inside this region, space-time is dragged around faster than the speed of light. It is impossible to stand still. You must spin with the black hole. This powerful effect has real consequences. It changes how objects fall into the black hole. Instead of falling straight in, they are forced to spiral in, like water going down a drain. For decades, frame dragging was just a prediction. It was an idea that lived only in the equations of Einstein's theory. Scientists believed it was true, but they had no way to prove it. The effect is so tiny that measuring it here on Earth seemed impossible. How could you possibly measure space and time being twisted by our planet's slow spin? It would require an experiment of incredible precision, an instrument more sensitive than anything ever built before. But scientists and engineers love a good challenge, and they began to plan a mission to test Einstein's strange idea. This mission was called Gravity Probe B. The plan was to send a satellite into orbit around the Earth. Inside the satellite were 4 of the most perfect spheres ever created by humans. They were made of quartz and were about the size of a ping-pong ball. These perfect spheres would be used as gyroscopes. The idea was to point these gyroscopes at a distant star and see if they stayed perfectly still. According to Einstein, they should not stay still. Over the course of a year, the direction of the gyroscopes should change by a very, very small amount. The predicted change was tiny, only 42 milliseconds. It is the size of a human hair seen from 10 miles away. After decades of development, Gravity Probe B was launched in 2004. It orbited the Earth for over a year, carefully collecting data. The scientists on the ground then spent years analyzing this data. Finally, in 2011, they announced the results. Gravity Probe B had detected the twisting of space-time. Einstein's theory of general relativity doesn't just predict that space gets warped, it also predicts that time itself can be distorted. Time is not a universal clock that ticks the same for everyone, everywhere. The speed at which time flows depends on gravity and on your motion. The stronger the gravity, the slower time passes. It's not just a theory. We see it every day. The clocks on GPS satellites have to be adjusted because time runs slightly faster for them up in space. Now let's take this idea to the extreme. Let's go back to our spinning black hole and its space-time tornado. The gravity near a black hole is immense. This means that time dilation is also immense. If you could hover in a spaceship near a black hole, your time would pass much more slowly than for someone far away. But the spinning of the black hole adds another layer of strangeness. The frame-dragging effect, the twisting of space-time, also affects the flow of time. It means that the speed of your clock would depend not just on how close you are, but also on the direction you are moving. Let's imagine a simple experiment. You and a friend each have a perfectly synchronized clock. Your friend stays far away. You fly into the ergosphere and travel in the same direction as the space-time vortex is spinning. You complete one orbit and return to your friend. When you compare your clocks, you will find that a different amount of time has passed for each of you. Your clock, having moved with the spin, will have experienced time differently. But what if you did the opposite? What if you used your powerful rockets to travel against the spin? This time, when you compare clocks, you will find an even bigger difference. Fighting against the twisted space-time would cause your clock to tick at a different rate. To truly understand the wild nature of space-time, we need to look at the giants, supermassive black holes. One powerful tool is gravitational waves, ripples in space-time from catastrophic events like colliding black holes. Another method uses pulsars, dead stars that act like cosmic lighthouses. By precisely timing their radio wave pulses, scientists can detect gravitational waves stretching and squeezing the space between us and them. Perhaps the most ambitious project is the Event Horizon Telescope, a network of radio telescopes creating a virtual telescope as large as the Earth. This incredible instrument has already taken the first ever picture of a black hole's shadow. In the future, we hope to see the hot gas swirling just outside the event horizon, allowing us to map the twisted landscape of spacetime directly. We live in a remarkable time. For thousands of years, we've looked at the stars and wondered. But today, we can build machines to probe the very fabric of reality. We've learned the universe is far stranger than our ancestors dreamed, a place where space can bend, time can slow down, and giant whirlpools of space-time spin in the dark. The journey of discovery is far from over, driven by a curiosity that allows us to reach out and touch the deepest wonders of the universe. Comment Galaxy for Spacetime PDF.